I'd like to welcome you all to our webinar today. This is on laboratory metrology, accuracy and precision, standardizing the terminology. My name is Jenny Bardsley, and I will be your host for today. I would like to introduce, oh boy, we're going to cut this out. It won't let me change. There we go. I would like to introduce Dr. James Blackwell. He is the president of Labshire, as well as Windshire Group. He's been a prominent industry consultant for over 12 years, where he's worked on a variety of quality issues for a broad range of companies and investors, all product types of all stages of the product life cycle. And prior to consulting, he had several senior positions in technical operations, manufacturing, and process development at prominent operating companies. And then before I do turn this over to Dr. Blackwell to introduce our presenters, I just wanted to let you guys know that during the presentation, we will be having a Q&A. So you can use the chat button or the Q&A on your panel and submit the questions throughout the presentation. And during the end of the presentation, we will answer any of your questions. So at this time, I would just like to hand this over to Dr. Blackwell.
Thanks, Jenny. I'd like to introduce Deborah Miller. She's a very senior consultant who's done has tremendous experience in medical laboratories and auditing QC and GMP manufacturing operations. She served a number of years at the American Red Cross, where she was managing a consent decree. And she's worked as a quality assurance manager for blood testing and director of confirmatory laboratory and director of compliance type of positions. She's been consulting for a number of years now and has provided excellent support to our clients. Mark Gusak is an MD, former nuclear medicine technologist, clinical engineer, and retired pathologist, and has had extensive experience working with the VA and their laboratory systems, and is very familiar with CLIA regulations and ISO 15189. And he has been extensively involved in metrology and the issues around accuracy and precision and how it can impact outputs from laboratories. So with that, I'd like to tee up the topic today. So I think all of us probably have some idea of what we mean by accuracy and precision. But knowing what is needed to achieve that really is a challenge for laboratories, because laboratories rely, it's the essence of the output of a laboratory, and then your customers, whether they're internal or external, rely on the accuracy and precision of your results relevant to their requirements and needs. But while we'll be talking about some of the specifics of those things, I also want to make the point that your operations and your quality systems and functions within the laboratory impact those results. So it's a holistic approach that needs to be taken to ensure the reproducibility and accuracy and precision of your measurements. So with that, Mark and Deborah, please get rolling.
Thank you very much. Let's get to the first slide. So, metrology, we're talking about measurement uncertainty, and in this case, we're going to talk about accuracy and precision. And one of the things I like to start off with is over the past 40, 50 years being in this field, I've noted that one of the major problems in establishing good metrology is establishing good terminology. And often you'll hear vendors and manufacturers talk about reliability. Our test system is reliable. And then the big question is, well, what does reliable mean? And so we're going to get into that. Next slide. And what we're going to do is we're going to talk about standardizing what these terms mean before we go on to the actual, measurement of these and attempts to control them in your laboratory. So the first line is for this is that this is the second in a series of presentations where we examine this term reliability, where we're going to focus on the concepts of accuracy and precision and how they influence it. And this is as opposed to sensitivity and specificity, which are really related to it, but not important at this time. Next. To do this, we need to define what accuracy and precision are so we can establish a shared understanding of their meaning. And this is really important. Lots of people think they know what accuracy and precision are, but in the literature, you'll find lots of different approaches to it and a lot of confusion with a lot of different terminology. So the next line, so we have the reliability of a test result and the impact on clinical, what?
I think we're on slide 8, Jenny.
Oh, sorry, guys.
Oh, she didn't hear me? I'm
No,
sorry.
I'm sorry, I didn't hear you. That's okay, continue on,
So-
thank you.
Yeah, what we could do is simply go, let the entire slide show up. So you can just click down until you get to the final line.
Yep.
So the reliability of a test and the impact on clinical and research results are really what we're talking about here. So this presentation sets the stage for future presentation on effective approaches to measure test system accuracy, test system precision, and determine their potential impact on what we call acceptable performance, which is based on accepted risk criteria, which the end user has to define so that the laboratory can choose the appropriate laboratory equipment, as well as to establish through qualification the accuracy and precision needed for that particular mission, for this purpose. So the next slide, and you can just go right down and show all of the headings, since I'm not in control at this time.
Sure, we're
So
all set.
first we want to talk about the mission of the laboratory. And it's really important that it's, the testing of specimens for the presence and or amount of one or more analytes, and then providing these results that are as reliable as they can be given limitations of test systems. And it's important to understand that no test system is perfect, that they all have limitations. And these limitations are quite global. They include, but are not limited to, the underlying physiochemical and biochemical principles of the test system, which will limit the degree of detection of any particular analyte and its ability to quantify that for the end user. The quality of the build of the instrument itself, because, as well as the supporting equipment and ancillary materials, because once you go to commercialization and you're building large numbers of instruments, no matter what kind of quality control you have, the instrument that you receive may not be as good as the ones that were used for FDA approval. Then there are procedural controls in place to monitor the reliability of the test system during routine operations. Because during routine operations, things are going to change. You're going to need maintenance, things are going to break down, you'll have drift in some of your components, for example, a sensor or a light, and all these can affect, depending on how they happen, both accuracy and precision. And then the processes used to run the test system under routine operating conditions. And this has to do with your procedures, your policies and procedures, and how easy they are to follow and how comprehensive they are. And then finally, the competence of the personnel operating the test system. If not been trained properly and they're not vigilant enough, you can have changes in accuracy and precision over time. Or perhaps when you qualify this system, because they don't understand it quite well enough, that they don't produce the kind of results that you're going to need. So we can't eliminate all of these measurements of uncertainty, and the recipient of the test result needs to be informed as to the following: what is likely a change due to the subject being tested versus what is likely change due to the capability and reliability of the test system itself, so that clinically you don't have a wrong diagnosis due to variability in the test system itself. So finally, this is really a determination of accuracy and precision, which are critical to the effort to do this. Next slide. So there are two cases regarding the metrology of a test system: the reporting of accuracy and precision of any single test result, and what you have in place to make sure that when that test is being run, that you're maximizing this accuracy and precision. And then monitoring of the accuracy and precision of many test results over time. That is, you're actually plotting, or you've got a software that will analyze to see if there is a subtle shift either in the accuracy or in the precision. So by analyzing these data, the laboratory can provide the following, either to a clinician or a research scientist. For the clinician, it means distinguishing an actual change in one or more patient analytes, leading to better understanding of their clinical condition. And for the research scientist, it means distinguishing an actual change in one or more test articles, leading to a better understanding of the condition of an experimental system. And what that means is that when you ascertain the accuracy and precision of a test system, it helps establish acceptable measurement error, so that what you've got is a limit on how far away you can be from a target value that you test to a standard or a control, and how often you get a significant variation from it on a single test application. So you can both look at individual test results and the reliability, as well as shifts in reliability over time. Next slide. So this is a slide that Deborah is going to go over for us, because she's got quite a bit of experience in FDA-approved tests.
Yeah. Okay, so when we talk about FDA-approved tests, most clinical laboratorians understand that that's a reagent system controls standards that are defined and approved by the FDA, and the CLIA requirements are defined for those tests. If it's a laboratory developed test, then the laboratory essentially has to behave like the manufacturer to meet the accuracy and precision requirements for CLIA. So for this presentation, we're just talking about the FDA approved test. And the manufacturer generally determines the accuracy and precision during the development, and it's in a controlled environment. They're not dealing with all of the variables that are included in the uncertainty measurement in an operating laboratory. They're pre-production systems, and they're set very broad. I used to tell my staff that the parameters are wide enough that the lab could drive a truck through them. They have to set them, or they choose to set them in wide ranges so that they'll be applicable to all different types of laboratories that might purchase their system. That means that their accuracy and precision values are only a starting point. This is very important. You will hear lots of times that laboratories say, well, our IQ, OQ, we met the manufacturer's requirements. And that's a baseline. If you are just meeting the manufacturer's requirements, you're right on the edge of falling out of compliance or out of the acceptable accuracy and precision if you're just meeting it. Therefore, you qualify the test, and that's your PQ, your process qualification, in your environment with your staff. I know when Mark was talking about variables in the laboratory, the other thing that can happen is a variation in the temperature in the laboratory can impact, like in the summer, if the temperature is not well modulated, and I've worked in some hospitals where the lab was in an area that wasn't well modulated, then that can impact the performance of your analyzer. In particular, the reliability of the specific instrument, the equipment, the FDA approved kit, all together with your staff needs to be established. And as I said, it occurs during the process qualification before you put into service. I'm currently looking at auditing or doing a gap analysis for a laboratory that's going to screen donors, not for blood, for another material. And they said they're already reporting results to the manufacturing plant. However, they're still qualifying the method. That's not a good way to go. And for research organizations, there's a parallel process for your technical operations requirement. You still need to know what your baseline accuracy and precision is, so that you can be the person or the laboratory that identifies potential problems as early as possible when you get a result, an out of spec result, or an atypical result in research, to cause you to go take a look and see if there's problems somewhere. And then an important part, once you establish the accuracy and precision, is to monitor your accuracy and precision. And I have a quick little story here, a real life story. And this was before software that would monitor your QC automatically. So I had a benchtop analyzer that I was doing serum blood alcohol levels in a Department of Defense laboratory. And the optimum number was 50 milligrams per deciliter, or to convert it to like a legal number, 0.05. And the test was being done to show fitness for duty. So if a soldier showed up for duty in formation and the commander suspected that they were under the influence of alcohol, they would send a test over. And if it was 50 milligrams per deciliter or higher, then the soldier had some kind of non-judicial punishment. So there was real impact and real consequences for the accuracy of that result. And our instrument, when we qualified it and did our process qualification, we came within the manufacturer's stated imprecision of 3.5 to 6.5%. Our imprecision was about 4%. And we operated this instrument like that for about a year. And then another thing that came into play, the competency of your employees. My particular technologist who was operating that bench came to me and said, there's something going on with blood alcohols. I can't figure it out. Sometimes the controls come in, sometimes they don't. And he went through all of the normal things that techs do. They open a new control, or they'll rerun it, open a new control, different things that you would normally do, and still couldn't figure it out. So I said, run a precision test. So he ran 11 repetitions of the same control, and the imprecision had jumped from 4% to 5.5%. And that was still within the manufacturer's stated range of up to 6.5%. So of course I contacted technical services and they said, well, it's still within our range. And I explained to them, yeah, but it's not within my stated operating range, which was around 4%. There was a jump. We're having problems, random problems with controls coming in. Excuse me. For no apparent reason. There was no change that we could find. So after much debate, they finally sent a field service person in, and he opened up the part of the instrument we weren't allowed to go in and found that the stepper belt, excuse me, the stepper motor belt that sampled the sample cup was frayed. So it randomly caught when it was rotating. Excuse me. So that's an example of setting your range, monitoring it, and having competent people who keep track of it and raise the flag when you have a issue. Next slide.
So I'm going to take back up. That's a really great example, and there are many others both Deborah and I have experienced with this. It's not uncommon for something to happen, including just something on a computer board slowly failing, a component, and that can be a sensor or a light, and that can be irregular, or it can be constant drop in, say, intensity or the ability to pick up the lighting, and all that can lead to changes in accuracy and or precision. So now we're going to get into the concept of measurement uncertainty and how this can affect somebody. In this case, we're talking about clinically. So inaccuracy itself, that has to do with systematic reporting something either too high or too low. And this is from a real case where at a laboratory, the hemoglobin A1C results were being reported out at around 7% for patients instead of the actual value of 6.5%. And that led to a lot of false positive diagnoses of type 2 diabetes. And so that led to a systematic increase in patients who were subjected to systematic treatment of any type, and in some cases over-treatment because the values of those who did have diabetes were too high, and therefore they were being over-treated. And that led to a rise in something called hypoglycemia, where their blood sugar is too low, and that is actually acutely very dangerous and can lead to death. The imprecision, which I've seen, is where you can even have high accuracy, no problems, with the actual target values, but periodically or sporadically, you have either a high or a low value, and that can lead to both the overdiagnosis and the underdiagnosis of the diabetes, and a sporadic over or under treatment of the diabetic patients. So if the test system is both inaccurate and imprecise, you can really be in great trouble. So next slide. So what we have here is something that I developed many decades ago and have improved upon over time, and that is looking at accuracy and precision first by visualizing it. And the target motif, which probably you've seen before, is really the best way to do this. I haven't seen anything better than this. And over in the upper hand side, left-hand side, we have the ideal, what everybody is shooting for, so to speak. You get a bullseye every time, both accurate and precise. So you really don't have to worry. And if you can maintain that, you're doing great. On the upper left-hand side, what you have is inaccuracy, but very great precision. So you're precisely off target. So every time you're always wrong, but you always hit the same area. In the lower left-hand side, you're imprecisely on target, but you can only correct this if the many hits are average. In other words, they all lie around the bullseye, and if you were to average them, they would be focused on the bullseye. There's this scatter effect, kind of like a shotgun. And then if you're imprecisely off target, well, that's the worst of both worlds. You just don't want to deal with that. So what we have with being precisely off target every time and always wrong is an opportunity. The laboratory can actually mitigate this by applying a correction factor to bring the results back to the target value so they look like the upper left-hand side. In the lower right-hand, with being imprecisely on target, you can mitigate this by executing a minimum number of duplicate specimens that you determine will give you a good estimate of what the actual average value would be. And this is something that was done very early on in the field of radioimmunoassays back in the 1970s and 80s. Those instruments were very inaccurate. And what would happen is that the laboratory would run the patient specimen many times, at least 2 times, often 3 or 4 times, along with controls in between each patient. And they would use that information to determine whether or not they've got a patient with a higher or a lower value for that particular test. The next slide, please. So we can also define textually what accuracy and precision are. So in the upper left-hand box, we have the term accuracy. You'll also hear terms like bias and drift. And what this is really accuracy has to do with a systemic error that occurs in testing over time. And we tend to use calibrators or standards to monitor this. And what we're doing is we're looking at how the components are operating, not really how the reagents are operating, but how the components are operating, and whether or not what the end result is what you would expect. And so you can have the failure of a conveyor, you can have the failure of a light, you can have the failure of an electronic component, of a sensor, and it can occur not immediately, in which case okay, it's not working. Instead, the light starts to dim. And I've seen this happen many times. Now, there are instruments on the market which monitor these things. The problem is those components that monitor the other components can also fail. And so you're not out of the woods with that. You have to still do your own monitoring. You have to still keep a track of it. And so the best definition I've seen of accuracy is the proximity of the average result to a reference standard. And that's regardless of the proximity of any one result, either to the other results or to the reference standard. So that you're really looking at a weighted calculation. Precision, on the other hand, is where you have individual events. You get randomness. People talk about dispersal or tightness. And here it's analytical. You're testing an individual specimen, and you run controls to monitor the system in real time. And in some cases, you'll run a control at the beginning of a batch run of many specimens, and then at the end, and it can catch a random problem with the test results perhaps not being fully precise because the controls are not in either at the beginning or at the end. So here the definition is the proximity of individual results to each other, and that's regardless of proximity of the average value to a reference standard. So we're taking the visual that I showed in the previous slide, and now we're putting it into words. Now, some people like to look at total error, the systemic plus or the analytic, or plus or minus the analytic. I generally don't use this, and when I'm talking with my clinicians, I try to avoid that because there's a tendency for them to become confused by this. But they generally can understand accuracy and precision as two different issues. Next slide. So I'd like to conclude that understanding the meaning of the terms accuracy and precision allows for the design of an effective approach to establishing the metrology of a laboratory test system. And that's whether it's been provided by a manufacturer or it's developed by the laboratory. Understanding that if it's developed by the laboratory, you don't have any of the manufacturer's prior information where they've done extensive data analysis of large numbers of specimens that have been run, which you can then look at where they've got target values and where they have a nomogram already set up to convert the signal to a final result. All sorts of things that you're going to have to assure is operating properly if you develop it in your own laboratory. And this will assure that you're choosing the right test method for the and system for the mission. That is the purpose. Are you clinically, are you screening for patients to see if they might have a disease? Are you confirming a diagnosis? Are you looking at the effects of treatment? Are you looking at trying to determine prognosis in a patient? Are you trying to look at their physiologic state and not make a diagnosis to see if you need to treat them, such as for their electrolytes, things like that? And you want to minimize the risk for deploying a test system that does not support that mission and maintain the reliability during routine operations to assure success of the mission. So it's a two-step operation. You establish the foundation, you get your numbers in, doing adequate performance qualification, and then you use that upon which you build the rest of this structure, which is the quality control and calibrator runs to monitor what's going on. And this is achieved by basing your decisions on end user stated acceptable measurement error. What's going to be something that they can handle, that they can agree to. Next slide. So in the follow-up presentation, we're going to move on to look at effective approaches to establishing a reliable estimate of both test accuracy and test precision for quantitative and qualitative test systems. Now, this won't be presentable all in one slide deck because we're talking about a couple hours worth of presentation, but we will do it in bite-sized manner, and then can put together a final PDF file for those who are watching this to use in their own work. And also, you have to monitor test performance over time to identify changes in the metrology. And you need to do it in a timely manner. You don't want to wait and do it on a monthly basis and find that the last month of data was out and you didn't realize it or it shifted. You don't want to wait until your researchers or your clinicians say, you know, we've been splitting these test results because we don't really, we think there's something wrong, and this other lab over here is getting a different result from you all. And so you assure that your test system fulfills the needs of your end user. Next slide. Any questions?
I'd just like to interject here, Mark. So when he talked about selecting the right test system for your mission, I can tell you that after I had the difficulty with the manufacturer on troubleshooting my benchtop analyzer for blood alcohols and their insensitivity to my mission, which was different than a legal mission for driving while intoxicated, I switched to a totally different manufacturer to a totally different instrument. So there was an example where the understanding of our precision and accuracy and operation of that assay had motivated me to switch to a different instrument that was reliable, and I didn't have any problems around 50 milligrams per deciliter. The other thing I'd like to let you guys know is that for R&D labs and GLP labs, you essentially, in most cases, are the manufacturer. You're the one that has to decide, develop, measure all of these performance criteria for these assays. So it's very helpful to look at the CLIA requirements and the medical lab requirements for this, to use that as a design of your protocol to develop and qualify your assays.
All right, thank you, Deborah and Mark. That concludes our presentation portion, and now we're just going to move on to the Q&A portion of the webinar. As I mentioned in the beginning, you can submit them through your panel, either in the chat or in the Q&A tab, and we will answer them as they come. I do have a few that came in during the presentation that I'm just going to pull up right now, and we will have our panelists help answer. Let's see. So Mark or Deborah, what do you include in the qualification when you say process qualification by the laboratory? And what is different or the same for this step for a research laboratory?
Well, when you do your process qualification, that means that you write your protocol to include all of the normal steps that you take with all of the normal variables, with all of the normal qualified people. You want to make sure that you cover the conditions that the actual samples are going to be run in long term. So you will be multiple days, multiple people. If you have more than one analyzer, you have to do your qualification process between the two analyzers and separately. Is there a difference between them? So you want to make sure that you include all of your variables for the process. This is very different than the IQ and OQ, which is just pretty much determining whether or not the instrument is installed and functioning according to the operating manual.
It also depends on the type of laboratory. So for an R&D lab, there can be varying levels of qualification. It depends on the purpose of that lab, what the data is going to be used for. But under any circumstance, an R&D lab, the methods need to be qualified to be scientifically sound, but maybe not in a formal approach. On the other hand, some of these laboratories, like a pilot lab, they may be relying on that data for GMP decisions, in which case I've seen those laboratories and the methods that are supporting them be qualified.
If we remember back to the CDC developing the initial COVID screening kits that were sent out and they failed because of one of the components wasn't correct, I'd love to see the deviation investigation on that, because I'm guessing the process qualification for developing that kit had some gaps in it, and they didn't catch that.
All right, thank you. A next question. Can you name one or more sources of inaccuracy and or imprecision in a test system and how they cause this to occur?
Yeah, we actually covered that in the presentation, but I'd like to go over it again because it's really important. So basically, your accuracy is going to be determined by either systematic changes in the components, the physical components of the instrument, or in systematic changes in the reagents that are sent to you to be used. So a change in lot number can lead to a change in how the system operates and can affect the accuracy. So one of the most important I've seen has been the sensors and the lights that are used. So you have a biochemical reaction with a color change. You need a light that will actually cause a sensor to pick this up. It could also be a fluorescent dye, and this leads to a signal, and then the signal is changed into an actual value, an amount of something that's in the specimen. And these often can fail slowly, and so that's really a key thing. That's why you want to run your calibrators and your standards. In terms of imprecision, What I find most often, it has to do with outdating of reagents or mishandling of reagents, or for example, they haven't been stored the way they should be. Some cases you can mix up a control, or you can start a control, open up a control, and you can leave it at the bench top, and it's resistant to minor changes in temperature. Others, they have to be put back into a refrigerator, and it can be, if it's left out too long over a period of time during the day or overnight, you end up with a problem.
Or in my case,
next question.
Wait, in my case,
Okay.
you could have an actual mechanical problem with the instrument that you can't see, which was the step remote. Or you could have as simple as a short sample with a standard. Something is in the well, or the well wasn't filled enough, and you get a short sample and you get an anomaly that you can't trace. Yep.
Okay.
And there can even be systematic problems. I won't name the company, but there was a company that had a hematology instrument that for years, if you set things up and ran your controls with an open tube of blood, you got a different result than if you had a closed tube of blood, which usually most labs would do. They'd have a closed tube for their batches. And it had to do with a problem with the draw up system, where if it was drawing from within a closed tube, it would draw less, and that the lower volume would lead to a systematic change in the accuracy of the outcome of the test results.
Thank you, Mark. For our next question is, how does one separate test system related variation in a single result from clinically related variation in a patient?
Yeah, so this is really the key to qualification of the test system and then ongoing monitoring. So first, you want to have an adequate number of testing of sample size of standards, of various standards, depending on exactly what the test is, quantitative or qualitative. And then you also want to run a number of regular specimens to characterize the system in terms of its accuracy, its baseline accuracy and precision. And then you can know, and you can even report out to the physicians that if a test result lies, so a patient may have a result, if they then have a second result, you're monitoring their therapy, say for hemoglobin A1C, if that test result changes by a certain factor that's below a cutoff, then it's most likely due to the instrument itself, and not to change their metformin or their insulin therapy, because you could over or under treat them, and to wait another 6 months. It's not going to hurt the patient, and do the test again. And if you get a string of 3 changes, then you have a trend that has been established. It's not due to some random error that has occurred, due to the testing system itself.
And
so
when
that's how that can be done.
And when you're setting those numbers, when you're running those multiple samples, you need to make sure that your actual values, your concentrations, cover the range that your patients might fall in. So the normal range and the reference ranges that are considered abnormal for your population.
And if you have a medical decision point, you should focus on that as well. And then as you go along, to maintain this, you can take have a running average and a running standard deviation in terms of calculating the precision of your control data. And so you can see, are we shifting, or is there a widening of this range? And first of all, you're going to investigate that and try to correct it. If for some reason, because of the change in manufacturing reagents, you can't correct it, at least you can tell your physicians, this thing is widened. And if you get a result within this new range, you're probably, unless there's something clinically that you can see that has changed in the patient, it's probably not a good idea to conclude that you've got a change in their clinical status.
All right, thank you, Mark. And we might have a heavy loaded question here that, who knows, we might need another webinar just to cover this topic. But if you guys can answer it, this is a big one. It's, what is the single biggest mistake labs make? Any takers for that one?
Mark, you want to start?
Yeah.
We can all
Yeah,
chime in.
yes, it's a lesson I learned in 10th grade from my mechanical drawing teacher that I didn't understand how significant it was. And there's just one word, assume. Assume as few times as possible. Sometimes you have to assume and speculate, but don't assume, find out. Actually, and another thing is that I had a resident in training when I was in medical school in the ER. And one day he got so frustrated, he erased, we used the blackboard, and he erased the whole blackboard. The nurses went nuts because they had all sorts of patient information on it in the different rooms. And he wrote the following words: in order to check these things out, ... you have to check these things out. In other words, don't wait. Don't just kind of see, oh yeah, this has moved. This accuracy has changed. No, check it out. Actually investigate it. So you don't assume, and investigate. If you do those two things, you're going to do a whole lot better and avoid lots of mistakes.
I think from my perspective, it's really when starting up and not planning ahead and putting together and thinking through everything and having a plan and putting together the proper procedures and policies in place and training everything you're going to need, and sort of assuming that things will just sort of run by themselves. So I think for startups and start setting up, I think those are the most probably common mistakes.
Following on to that, James, I would say that as part of your startup is to define your process in very tedious detail. I do a lot of audits of laboratories, and when I ask them, start me when you receive the specimen or the test article and walk me through it, I can tell right away whether the laboratory is in control or not. If they can do that and they can give me all of the detail, then I think that they've done a good process map. But if they look at me like with shock in their eyes and say, well, what do you mean? Or they give me a very high level, we get the sample and blah, blah, blah. I mean, I've asked labs, how do you label it? What's your requirements for labeling the internal samples? And I get a blank stare. Those labs have not mapped their process in detail. Mm-hmm. And if you don't map your process in detail, then when you try to go investigate something, you're going to have a lot of gaps.
I think another one we talked about
that really brings
for the webinar was not understanding your user requirements, your customer requirements, and accuracy and precision that they need. So, and that can work both ways, right? You don't want to have a method where you spend a lot of time and effort that's overly precise, overly accurate when it's not needed. On the other hand, probably the more common mistake is you have one that doesn't have the accuracy and precision that your customers need.
Lots of room for mistakes in labs.
Yeah. And so this really all brings up a subject that was developed out of the same problem that occurred with weapons in World War II, and that's failure mode and effect analysis, where as Deborah and James have said, and I have kind of implied, you need to look at your system, you need to look at your processes, you need to look at all your tools, that's the test system itself and all the ancillary equipment and reagents, and you need to look at your people and making sure that they understand the processes, they know how to use the tools properly, and they follow the system, the logic of the system, so that if something happens and there's a branch point, do we release this test or not? They know how to handle it, how to investigate it, and then kick it up to the next level when they can't solve the problem.
All right, well, thank you, Deborah and Mark and James, for answering the questions. If anybody else has any questions, please feel free to email us at info@labshire.com. But we are getting to the end of the presentation. As we've noted, we will send you a link to the presentation afterwards, and we will also have it available on our website at labshire.com. And please stay tuned for upcoming webinars. Deborah and Mark are gracious enough to be doing a series on these laboratory metrology webinars. This topic's quite robust, so they'll be covering a lot of information. And then lastly, I would just like to pass it along to James for some closing remarks.
Thanks, Jenny. Thanks, Mark and Deborah. And as everyone has seen, Mark and Deborah are outstanding consultants with deep expertise and experience. So they and our other consultants, if you have any laboratory issues or other consulting issues you'd like to run by us, we'd love to hear from you. And I'm sure that we could help. And thank you for attending.
All right, that concludes our webinar for today. Thank you.
Thank you.
Bye-bye.